He's going to talk about on singular perturbation of the Morse complex. Thank you.
Thank you, Jose. So before starting, of course, I would like to thank the organizers for having invited me to speak here. I've seen some impressive talks in this conference so far. Anyway, today I'm going to talk about singular perturbations of the Morse complex. So, what's this about? Amongst various other things, I'm interested in Morse theory. Ever since I first saw Morse theory whilst I was doing my PhD 10 or 15 years ago, I was always impressed by how beautiful it is. On the one hand, you have families with solutions to partial differential equations, and you can extract information about these families, and this information can be expressed in a very pure algebraic form. And that pure algebraic form of this information takes the form of Morse theory. And it's a remarkable and concise algebraic expression of the relationship between different solutions of different PDEs. So what goes on? Well, let M be a compact manifold. Everybody knows how this works. We imagine we have a manifold like this. Then we take a function h. H is a function that sends M into R, which we conceive of as a height. We say that H is of Morse type whenever every single one of its critical points is non-degenerate. In addition, we can say that the function is of Morse-Smale type when not only every single one of its critical points is non-degenerate, but also every complete integral curve of its gradient flow is also non-degenerate. What does that mean? Well, you can look at the perturbation operator of a complete integral curve of its gradient flow. It's a finite dimensional parabolic operator, so it's because the endpoints are non-degenerate, this thing will be Fredholm, and then you can talk about whether it's surjective or not. It's quite easy to find functions of Morse type, they're dense, and it's equally easy to find functions of Morse-Smale type. They're also dense. That's not too difficult to prove. So, the great observation of Morse, the beautiful observation of Morse, is that critical points of H are related to a topological invariance of M. And this forms the basis of Morse theory. Now, in the original work of Morse, people tell me, I haven't read it, but in the original work of Morse, there are already indications of the deeper and more beautiful Morse homology, which is a more subtle expression of Morse theory. The idea is that these critical points actually constitute a chain complex. And this chain complex has a homology, which you can study. The idea is the following. Imagine we have our critical points of the height function. They're here, 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 and here. For each k, we let xk be the number of critical points of Morse index k. So we see that these two critical points have Morse index 2, so there are 2 of them. This critical point here has Morse index 1, there's 1 of it. And this critical point here has Morse index 0. So we have these 3 different sets. H2 is here, it's this pair. H1 is here, X1 is here, it's this one, and X0 is here. Then, what we do is we define vector spaces. All right, yes, I'm sorry, I should say. For any x in xk plus 1, and for any y in xk, for example, x could be this point here, and y could be this point here, there are only finitely many trajectories from x to y. This is a consequence of the fact that the function is of Morse-Smale type. This is an analytic result. It takes a little bit of proving. So, for each k, we use these xk's to define vector spaces. They are quite simply the set of functions from xk into z, if you want to do z-based homology, or in the simpler case that we're studying here, the set of functions from xk into z2. I like to use this, most people use this algebraic notation, where you write z2 xk, but it's actually the same as the set of functions f, which send xk into z2. This is more concise. Now, the point is that you can define an operator d, and this operator d sends zk plus 1 into zk. Now, I don't want to spend too much time developing Morse theory. I'm going to assume that most people have a fair idea of what's going on. I want to talk about other things afterwards. But the point is that this operator zk is defined in terms of the number of curves that move from a number of curves flowing from points of xk plus 1 to xk. And we know that there are only finitely many, so we have numbers here that we can use. So that gives us this d. And the remarkable thing is that the square of this operator is equal to 0. What does that mean? That means that this complex z star d has a well-defined homology. So we can talk about its homology. And we call this the Morse homology, MH, of the manifold. When M is compact, this is canonically isomorphic to the singular homology of the manifold. So you can interpret this in two different ways. This means that, on the one hand, you can use Morse functions to determine the topology of the object you're studying. Conversely, if you already know the topology of the object you're studying, you can also obtain information about the number and the nature of critical points. Now, why is that? Well, the point is this. For each k, the dimension of zk is bigger than the dimension of the corresponding homology group. Why? Because the homology group is a quotient of the chain group. But the dimension of zk is quite simply equal to the number of elements in xk. So the dimension of the homology group for each k will tell you exactly, will give you a lower bound on the number of critical points of Morse index k. So, for example, in this case here, we know that we're dealing with a sphere. The homology of the sphere is h2 is equal to z2, h1 is equal to 0, h0 is equal to z2. This tells me then that for any Morse function, I have at least one critical point of index 2, at least one critical point of index 0, and I don't know anything else. And we see in this case I have 2 of index 2, 1 of index 1, 0 of index 0. How does this affect us? Why am I interested in this? I'm interested in studying immersions, generally speaking, immersions of constant curvature or immersions satisfying elliptic PDEs. Now, let sigma be a compact surface, usually a sphere, and let E be the space of smooth embeddings of sigma into M. So E is this. It's a space of embeddings which send by sigma into M. Now, usually quotient out by the group of diffeomorphisms. So we're actually interested in reparametrization equivalence classes of embeddings, but most of the time you don't say that because it's a bit of a mouthful. So when you mean smooth embeddings, you actually mean reparametrization equivalence classes. Let A be the area functional. So A is this mapping which sends my space E into R. So we're going to pretend that this mapping is of Morse type. We're even going to pretend that this mapping is of Morse-Smale type. When this mapping is of Morse-Smale type, then we should have a Morse homology. So, what are the critical points of this functional? Everyone knows what the critical points of this functional are. The critical points of this functional are the minimal surfaces. What are the gradient flows? The gradient flows are mean curvature flows. But they're not just mean curvature flows. They're quite special mean curvature flows. They are eternal mean curvature flows. This means that they are mean curvature flows that are defined for all negative and all positive time. Now, just as in the finite dimensional case, the Morse homology of this infinite dimensional manifold, MA, will yield information about the number and nature of minimal surfaces in M which are diffeomorphic to sigma. That is, not only should it give us a lower bound in the number of minimal surfaces that we have in our manifold, it should also give us a lower bound of the number of minimal surfaces of given Morse index. So it gives us information about the stability of the minimal surfaces that we found. Problems. Serious obstacles. And I have to admit, half the time I don't believe in what I'm talking about because the obstacles are big. Problem is that the theory to date is poorly developed and appears to be very hard. It requires compactness results for families of minimal surfaces of bounded Morse index. These are still forthcoming, though in certain cases you can get some quite good results. Some very good results, actually. But the really hard bit is it requires compactness results for families of eternal mean curvature flows. Flows which in general do not satisfy any convexity condition. This is a big problem. Because if you remember the talks that were given earlier this week about mean curvature flow, usually when one studies mean curvature flow, one assumes some form of convexity. Usually one assumes at the very least mean convexity, and then one takes that in order to prove convergence in finite time. But what do we have in our case? We know for a fact that we do not have any form of convexity. The main reason being that our flows are eternal. They do not converge in finite time. So what we are studying is exactly complementary to most of what is currently known about mean curvature flows. This means that practically none of the results we have to date on mean curvature flows are of any use. Though not all. So, why am I interested in this? Well, my guiding light, if you will, and my long-term objective is this very nice-looking conjecture. You take a Ricci positive free manifold. In this particular case, there's the work... Oh, hang on. In this particular case, work of Choi Shun gives us compactness results for families of embedded minimal surfaces. So we've got that bit down. So we've got the critical points, no problem there. And we have this conjecture. For generic G, there exist at least 9 distinct embedded minimal tori in M3G. So I like to call this conjecture the White conjecture. I wrote to Brian White, asked him if he was okay with that. I think he said he was. The point is, this is there in his work of 1991. It's not explicitly stated, but everything that he says basically points towards that. So why? Why 9? Well, the point is, if you look at certain special cases, you realize that the Z2 homology of this thing should be the same as the Z2 homology of the product of 2 copies of RP2. And what's the Z2 homology of RP2? The Z2 homology of RP2 is quite easy to calculate. It's Z2, Z2, Z2. There's 3 of those. You take the product of that, you get something which is 1, 2, 3, 2, 1. Sum of that is 9. So this tells us in particular that we should be expecting 1 stable minimal torus, 2 of index 1, 3 of index 2, 2 of index 3, and 1 of index 4. It's a more tractable problem where the analysis is a little bit easier, which seems to be more promising. Following. Let M be a compact Riemannian manifold. Let sigma M be the M-sphere. Instead of looking at tori, we're now looking at spheres, hyperspheres, codimension 1 spheres. And let E be the space of smooth, locally strictly convex Alexandrov embeddings of sigma into M. Okay? And let F be the area minus volume functional. So this is an area minus some constant times the volume contained inside the surface. It's Alexandrov embedded, so volume is well defined. And this is the functional one usually studies when one wants to study CMC surfaces. So the critical points of this thing will be the CMC spheres. CMC, constant mean curvature spheres. Now, critical points of this are constant mean curvature spheres. The complete gradient flows, instead of being mean curvature flows, they are now forced mean curvature flows. There's a forcing term. What that means, I forgot to write down the equation. What that means is that at any time, the normal component of the variation of the immersion is equal to some forcing term minus the mean curvature. In mean curvature flow, the forcing term F is 0. Here we've got forced mean curvature flow, the forcing term F is non-trivial. So, the main point of this expose. Wait, what time did I start, Jose? It was 35. Right, 50 minutes. We're halfway through. Okay. The main point of this expose is we claim that for large values of the mean curvature, so for large values of the forcing term f, the Morse complex of the scalar curvature functional perturbs to approximate the Morse complex of my infinite dimensional manifold. So you can calculate. So if you could show that there was a Morse homology for this functional, which you actually can do in certain special, very special cases, then not only do you know the existence of a Morse homology, you can calculate the thing. So, where does this come from? This starts with work of Yi, nice paper of Yi in 1991. Let's assume that the scalar curvature function of my ambient manifold M is of Morse type. This can always be achieved by a very small conformal perturbation of the metric. No problem there. There's lots of those. Let P be a critical point of S. And let Sm, sigma m, be the sphere of unit radius in TPM. And for all s in 0 infinity, we consider this embedding. So here, s plays the role of a scaling factor. As you see, as s tends to 0, the radius of this thing will tend to 0, but also the size of the perturbation tends to 0. So let's draw a picture to have a clearer idea of what's going on. So, we have a point here, and we have a sphere. This sphere will be of radius s. And then the function f defines a perturbation of the geodesic sphere about that point. And the size of the perturbation is roughly equal, well, to s times s squared, s cubed. So we're taking little perturbations of these things. And Yi's theorem says, if you start with this family, then you can perturb them to get constant mean curvature spheres. So that gives me the critical points in my Morse complex. I can't remember if I actually put Yi's theorem into this. I think I actually forgot to state Yi's theorem in the talk. That's a shame. Where are we? So the point, what Yi's theorem says is that if you have these spheres, you can perturb, for sufficiently small values of s, you can perturb them to get spheres of constant mean curvature, which are close to critical points of the scalar curvature functional. So imagine that we have a manifold here, we have my scalar curvature functional, then we know that radial spheres around the critical points of the scalar curvature functional perturb to give me CMC spheres, constant mean curvature spheres, which are the critical points of my area minus volume functional. So that gives me the critical points of my Morse theory. In actual fact, we have to do a little bit more, because it's not quite that simple. Because as the scale parameter vanishes, different functions which are dependent on this embedding, they vanish at different rates. This was one of Yi's observations, technical problem. So for this reason, it's actually convenient to displace the center of our embeddings. So what we do is we introduce a vector y, and we now look at this thing here. So what is that? So again, we start at a point P, but we have a vector y here, and we just move in the direction of y, like that. And we parallel transport. This t here is parallel transport along the geodesic from P to the point y. And we just parallel transport everything along this geodesic. So our new center is here, our new sphere is here, and all the data is parallel transported so that everything is now centered about this new point, which is the image of y under the exponential map. So this introduces a displacement of the center. And the reason why we do this is to compensate for the fact that different things are converging to 0 at different rates. And now we define this function h. And h depends on s, y, and f, is simply the mean curvature of this embedded sphere, this thing here, at that point x. Okay? So the point is, we want to make suitable choices. In order for Yi's construction to work, we want to make suitable choices of y and f so that h is constant. So this is notationally, this particular work is notationally quite a headache because there are a lot of terms. You're working in Hilder spaces. You have to do your Hilder estimates. There's a lot of work. There's a nice way of cleaning up the notation quite conveniently, and that is to introduce the notation of asymptotic expansions. So just have a look at asymptotic expansions. How do these things work? Let E be a finite dimensional vector space. Let phi be any smooth time-dependent or scale-dependent function. And let phi p k be a sequence of functions where for all k, phi k sends ek to r. Now, we let psi sheesh be a formal power series taking values in E. Then we have this statement here. Phi of s to psi sheesh is equal to this sum. This means that for all n, there is a smooth function Rn, which is simply a remainder term, such that this holds. So it looks very much like Taylor series, actually, but it's a little bit different. But in your head, imagine that this is Taylor series and that Rn is just a remainder term in the Taylor series. The important point for us, the really fundamental important point, is that the remainder has to be smooth at s is equal to 0. Now, why does this help? Because it means that we can, it helps because it means that we can use some nice theorems. It says, suppose we have a smooth function, f smooth. Okay? Then the mapping, which sends a function little f to the composition of f with f, well, for all k greater than 1, this defines a smooth mapping from ck alpha to ck alpha. Okay? So, we actually work with finite dimensional things. We develop our asymptotic expansions over finite dimensional manifolds. Then we have this remainder term, which is a smooth function. We have more information about the smooth function. And because it is a smooth function, we now apply this nice little theorem concerning sizes of, concerning estimates in Hilder spaces, and that automatically gives us the estimates we want. So we just hide the dirty work in Hilder spaces behind this smooth function. Cleans a lot of things up. So this is where, sorry, I said notational complexity. This is where it starts. So Ye's theorem is based on this asymptotic expansion for the mean curvature. We start by defining G. So G is the mean curvature minus 1 over s. So it's the difference between mean curvature and what we want. We want the thing to have constant mean curvature equal to 1 over s, then divided by s again. You can show that the asymptotic expansion of this thing is equal to this. And what we want to do then is we want to take y, we want to choose y and f in such a manner that this thing is equal to 0. Let's have a look at a few features of this equation, the ones that really matter. Notice that in each term of order k, we only have the k minus 1th term of y. Y only goes up to k minus 1. Also, note that this k minus 1th term of y is actually quadratic. And that plays an important role in what follows. Because, as I said, different things tend to 0 at different rates. So, let us take the space of first-order spherical harmonics. We're now going to decompose things. You let pi be the orthogonal projection onto the space of first-order spherical harmonics in the sphere. You can explicitly calculate it's that. Okay? And let pi perp be the other bit. Then, we take the orthogonal projection onto spherical harmonics, we divide by s squared, and we take the other part, and we obtain this. Because what's happening? So here, we have this term of order k minus 1. So we've got one factor of s here. But this is quadratic. So it projects to 0 on the spherical harmonics of order 1. So this disappears. So when you look at the spherical harmonics of order 1, you only get terms of order k minus 2 in y. This gives you a factor of s squared, which you can then divide out. And what you're left with is this, plus something which is of order 0. But that doesn't matter. The point is this. remember that our scalar curvature function is of Morse type. That means that this matrix, SAB, the Hessian matrix of S about P, is invertible. This thing is invertible. And this thing is invertible on the orthogonal complement of H1. So this whole thing is invertible. And that essentially is what you do to get the to find the solutions, to find that pair F, Y, such that this discrepancy G is equal to 0. Point is, it's actually a regular perturbation problem because you're always dealing with the same operator. So once you make the appropriate transformations, Yi's problem becomes one of regular perturbation. Now, let's just do the same thing in the parabolic world. Jose, how am I for time?
10:15.
Oh, great. I was worried. Okay. So we're now going to do the whole thing again in the parabolic world. Now, we let gamma be a complete object, a complete orbit of the gradient flow of S. Actually, I made a little mistake. You have to rescale things slightly. You actually require that the derivative of gamma be equal to minus m plus 1 divided by 2 m plus 3 times the gradient of S. Small difference. So we assume that at minus infinity and at plus infinity, gamma converges towards critical points of the scalar curvature functional. Now, what we're going to do is we look at the pullback of the tangent bundle on gamma. So we've got our manifold here, two critical points here. We have our gradient flow of the scalar curvature functional, gamma. So we have a look at the pullback of the tangent bundle of M, and by parallel transport, we identify this with R times Rn plus 1. And we're just going to define Yi's function, Yi's embeddings in exactly the same way as before. The only difference is that now it's time dependent. So for each t, our spheres are now centered about the point gamma t. So we have a family of spheres like that, centered around my geodesic. Now, in exactly the same way as in Yi's case, we also have this problem where different terms converge to 0 at different rates. So, again, it's useful to displace. And since in the elliptic case we displace with a vector, in the parabolic case we displace with a vector field. And then with G, defined as before, remember, G is a discrepancy of the mean curvature. We now add this term, which measures the normal component of the variation of the immersions. Okay? This term V represents the variation of the immersions. That is, V is equal to the time derivative of the embedding. Remember that the forced mean curvature flow equation is that the time derivative, the normal component of the time derivative of the embedding is equal to the forcing term minus the mean curvature. Okay? Now, here's one feature that you notice. I'm actually introducing a factor of S into this bit here. Why am I doing that? Well, actually, it makes fair sense. Because what's happening is, we're always moving along the geodesic at constant speed. Okay? However, for all S, the mean curvature of these little spheres, it's approximately 1 over S, okay, which is very big. So a priori, one would imagine that if we were using mean curvature flow, we'd be moving faster and faster and faster. But no, there's a forcing term. Forcing term is 1 over S. So we remove that. The remainder, it turns out, is of order S squared. So we actually have this remainder term in the mean curvature, which is of order S squared. And if you recall, in the definition of G, where did we do this? We divide out by S again, so that gives me a factor of S. So what that means is if I have a look at the discrepancy, if I have a look at this thing, in actual fact, if I have a look at the discrepancy with the mean curvature, its effect is that we're moving along the geodesic slower and slower and slower and slower as s tends to 0. Okay, and this is why we need this factor of s here. And this fact that we're moving along the geodesic slower and slower and, geodesic trajectory slower and slower and slower and slower, this is going to give us a problem. Why does it give us a problem? Well, you do use work again. You get here. This is our asymptotic expansion for this thing phi. Phi is the mean curvature flow operator, this thing here. Okay? When this thing is equal to 0, my y and f give me a forced mean curvature flow. Again, we have this nice phenomenon where you will notice that the order k minus 1 term of y is quadratic. So when we take the projection onto the first order spherical harmonics, we know this will die. So, and you see that the only remaining terms of y are of order k minus 2, so we're going to get that factor of s squared that we want. And we see then, we now define y pointwise for all pi pointwise for all time as a projection onto h1. Again, we get this sort of relation. Okay? We've got a problem. So, the mean curvature, the scalar curvatures of Morse small type. So this thing is an invertible surjective parabolic operator. But if you restrict attention to a finite codimension subspace, this bit here is invertible. But look what we've got here. We have this factor of s to the 4th that appears in the equation. If you notice, actually, this is one feature of this asymptotic expansion that you have to be careful with, is that the time derivative of f always comes accompanied with an s to the 4th. When you look at it naively, you would have put this s to the 4th up here with s to the k. That's not right. The correct operator to look at is s to the 4th dt, which is why you see another factor of s to the 4th appearing here in the remainder terms. This should be an s, not a t. That's a problem, because actually the problem that we're dealing with here is not a regular perturbation, it's actually a singular perturbation, because in the limit, as s tends to 0, the time component vanishes, and we no longer have a parabolic operator. So these operators are not uniformly parabolic. Still, you can more or less go in the same direction as E. So firstly, you have to do formal solutions, okay? So what you can do is you can find canonical sequences, ysk and fsk, such that in an asymptotic sense, this function is actually equal to 0. So these sequences, y and f, they essentially present formal solutions of what you're actually looking for. You've got to be careful, though, because the terms in the asymptotic expansion also depend on s. Now, why is that? Because they are determined by inverting s to the 4th dt. They're determined by inverting this operator. And because this operator depends on f, the solutions also depend on f. But this is where we have to be careful, because we want uniform bounds in the C1 alpha sense. But we have this horrible operator, which tends to 0. Naturally, the solution is to choose weighted Sobolev spaces. Okay? So we have our weightings in the derivative exactly to compensate for this s to the 4th factor. And then, magically, actually, everything turns out quite well. What was I going to say? Achieve these various weighted Sobolev spaces and a careful argument involving spherical harmonics. We also have to be a little bit careful with the remainders. This term here, phi k, this isn't actually the remainder term. This is another term which I just put together because I don't want to write out everything. You can show that this term phi k is a finite order polynomial in the curvature function and the metric. In particular, what that means is that this will always be a spherical harmonic of finite order. Well, it's actually a smooth family of spherical harmonics of uniformly bounded order. Why is that interesting? Because when you have a look at the inverse of this operator and you restrict attention to spherical harmonics of uniformly bounded order, you actually get better estimates. Because the norm estimate of the inverse of this operator looks like that. that goes to infinity. Not very quickly, but it goes to infinity. But when you restrict attention to finite order spherical harmonics, this thing is uniformly bounded, which is quite nice. It makes things simpler. But anyway, because we have our asymptotic series here, what this means in concrete terms is that for all n, there exists a constant. We apply this nice theorem here, which packages all these Hölder estimates very cleanly, and we realize that for all n, there exists a constant such that this thing is less than or equal to Cn times Sn to the s to the power n plus 1. Then you let Gs be the Green's operator of this thing here. This is time dependent. This is a scale-dependent thing. You can show that the norm of Gs is bounded by s to minus 4 alpha. So it goes to infinity, but frankly, it does not go to infinity that quickly. And you just choose a sufficiently large value of n to ensure that the error is small. You don't even have to go very far to get something which works. And then you simply apply the inverse function theorem, and that will give you a vector field y and a function f such that this functional phi s ys fs is equal to 0. What does that mean? That means then that for sufficiently small values of s, we have our critical points, which are constant mean curvature spheres. These are provided by Yi. We take our trajectories. Doing our parabolic singular perturbation, we can turn our trajectories into mean curvature flows. You can show that there are finitely many of these, and basically the Morse complex of the scalar curvature function transforms in this manner into at least a portion of the Morse complex of this infinite dimensional manifold that we're interested in studying. And this is something that is yet to be proven, but I don't think should be too hard. It's to prove the converse. That for sufficiently large values of s, in fact, these are the only eternal force mean curvature flows with that forcing term in the manifold. And what that would mean is that the perturbation of the Morse complex of the scalar curvature functional is exactly the Morse complex of the space that we're interested in. So that's everything. Thank you very much for having listened.
Thank you.